Just for not giving the impression to mathematicians that I am not a mathematician, we start today with the most technical part of our lectures. So we will talk about discrete models in mechanics. You know? So today we start with this. Discrete models in mechanics. Now, if you will start discussing with me about the content of these lectures, we will conclude soon that actually we are not studying discrete models in mechanics. We are studying discrete models in science. It happened that at the beginning of my career, I was professor of mathematical analysis for social and economical sciences. And I discovered that Lagrangian mechanics, about which I will talk to you now, is indeed the basis of modern economical science. So, this is very important. This is one of the reasons for which I ask you 10 or 15 more hours. I don't want to stop telling you ideas about what we are doing. Okay? Now, Lagrangian mechanics actually is a general method for describing natural phenomena. And Lagrangian mechanic ideas have been applied in many different fields. Mathematicians are working for understanding what is common among different parts of sciences, finding the common mathematical tools for studying these different parts. Okay? So, the reason for which sometimes mathematicians say that we don't worry about applications, it doesn't mean that applications are not important. It means that I don't want to be obliged to limit myself to one application. If my mathematical tool works in different applications, I want to distillate the common ideas of these different sciences in a mathematical theory which works for all of them. Okay? Now, why I'm telling you this? Because I will give you now the distillation of a modeling process which is used in many different fields of knowledge. Okay, so first of all, we talk about configuration. What is the space of configurations? The space of configuration is a mathematical object which is invented, which is introduced in order to describe the state of the physical system we are dealing with. I give you an example. Consider the mathematical model material particle. I'm sure that you have studied somewhere in physics the concept of material particle. Okay. Now, the model material particle requires the determination of three coordinates in a Cartesian system, x, y, and zeta, and you say that the configuration of the material particle is known when you know these three parameters. Okay. In 2 days, we'll spend 4 hours talking about these delicate issues. Okay, we will go deeper in this. Why? Now, I just tell you a hint of what we'll discuss. Is the Earth a material particle? It depends. In the motion around the Sun, the Earth is modeled as a material particle. So the configuration of the Earth is well described by the three coordinates x, y, and zeta. If instead you want to study the seasons, you cannot model the Earth as a material particle. Why? Because in order to understand what are the seasons, you need to model the Earth as a rigid sphere, which is turning around an axis. You discover that the axis is not orthogonal to the plane of the trajectory of the Earth around the Sun, so that depending on the season, there is more or less energy arriving from the Sun on a square meter of Earth, so it is warmer or colder. So the same physical object can be modeled either as a material point or as a rigid sphere which is turning around its axis and moving around the Sun. You should never confuse your mathematical model, which is invention of our brain, with the physical object. These are two completely different things. The mathematical model works in some specific situations to describe, to predict the behavior of the physical object. But not always. Okay. All paradoxes you find in physics or mechanics are not true paradoxes. You try to apply a model in a context in which this model is not applicable. Okay? But we will come back to this in 2 days. So in general, we call a discrete model a model in which there are n real parameters which characterize the configuration of your system. So, in the case of the material particle, you have 3 coordinates. In general, you need n coordinates. N is the number of degrees of freedom. The number of degrees of freedom is exactly the number of parameters which you need to introduce for describing your mechanical system with this, or your physical system with this space of configuration. These Q's are called Lagrange parameters or coordinates. Now, I will be soon bored and I will write Qi I between 1 and n for writing this, or I will be so bored that I will write q, meaning all of them. Okay? Okay, so the kinematics of our model is perfectly understood when you have fixed the Lagrange coordinates which characterize the configuration of your system. In the discussion you had with Dr. Barchiesi, I think, you have seen so-called Encke model of a beam, right? I think that in the lecture did you study the beam as a set of bars with springs or not? I have the video recording of this lecture, so don't try to say that it is not true. Okay? So you have rigid bars with these springs. Okay? And this is a discrete model for a beam, inextensible beam, if the bars cannot be deformed. And what you have understood is the following. I can block the first bar, then I need the first angle theta 1, then I block the second angle which is theta 2, then I block the third angle which is theta 3, and so on. So in order to know the shape, the configuration of this system of bars, I need to know n angles. These n angles are the Lagrangian parameters of the system, which we have introduced. Okay? So I have given to you already 2 examples. So, a system of n parameters which characterize the state of a given system are called Lagrange coordinates, and we have given to you the example of a material particle. A material particle is a system, a model with 3 degrees of freedom, and I have given you the example of a system of bars with pivots interconnecting them, moving in the plane, and this is another example of finite dimensional model, and the Lagrangian coordinates are these n angles. You remember that you have seen this, I hope. Okay? You should not believe that only physical models, only models for physical phenomena are available in the literature or are usefully used by mathematicians. Okay, before I go ahead, I must tell you that I have problems with the word physics. I explain you why. Physike in Greek means what is in the nature. So also an economical system is physics for me, because they are in the nature. However, in history of science, physics limited its applications only to certain phenomena. Now we call physical phenomena electromagnetism, quantum mechanics, electrodynamics, mechanics, hydraulics, and we don't call physics the study of an economical system. However, I want to give you an example of Lagrangian system from economy, so that you understand that these conceptual tools are much more powerful than you could expect. Did you know that before Euro, the countries of European Union had each a different currency? Okay? The economists studying European Union introduced C1, C2, C3, C28, the exchange rate of each currency with respect to the dollar. And they studied the evolution of the European economical system as a system described by a discrete system whose degrees of freedoms were at least 28. Why I say 28? Because somebody said, no, you should add, in order to characterize the state of the system, you must add also P1, P2, P28, the gross national product of each country. Then an economist said, no, this description is not careful enough. In order to characterize the state of the system, you must add D1, D2, D28, the debt of each of the countries in European Union. And then they said, no, you must add another parameter, unemployment rate. So U1, U2, U28. Of course, you understand that we can continue with this philosophical consideration without ending. Now, which is the capacity of the clever scientist? To understand which is the minimum number of Lagrange parameters which are sufficient for predicting a given phenomenon, for describing correctly a given phenomenon. Okay? This is the reason for which I don't give you n equal 300 or n equal to 2 millions or n equal to 3. Because we don't know in a given particular applications how many degrees of freedom are really needed for describing correctly the kinematics of that system. When we do this, we are mathematicians. Mathematicians are developing models which have a wide range of applications. Okay? By the way, a group of more or less clever engineers sometimes told me that I was crazy in introducing n degrees of freedom, because a true engineer is studying the motion of particle in space. So n equal to 3 was enough. Okay, God should forgive them. Because this example of bars with pivots gives you an example of a system of degrees of freedom 20, which is very important for engineering. Okay? Okay, now I stop here and we will go back to this subject in the long 4 hours we have on Thursday. Okay? So we have fixed the degrees of freedom. Okay? Now, next step is, what is a motion in this model? Okay, a motion, by the way, you should know that Demosthenes was, I don't know if, I will try to teach you also something which is typical of Europe, and maybe not all of you know about Demosthenes. Demosthenes has been the big politician and rhetor of Athens who established the rules of how somebody should talk in public. He discovered that the attention of the audience must be relaxed every 10 minutes. Otherwise, you lose the contact with the speaker. So I more or less periodically stop. Okay, this is not because I like to joke. You know, somebody told me that I like to make jokes or to waste time. I know that it is useless pushing you to be attentive for more than 10 minutes. So one has to relax a little bit. And then we attack the next step. I give you an information. Lagrange is Italian. Was born in Italy, in Turin. His true name was Lagrangia. For this reason, in English, you write Lagrangian mechanics, not Lagrangian mechanics. No. Lagrange is the genius who invented the theory which I'm describing you now. To my knowledge, this theory was not available before. Of course, it could be that somebody did something before, but to my knowledge, I've read carefully the sources. The theory I'm describing you is exactly the theory written in the books by Lagrange. In the last version he wrote before dying in 1801. Okay? Sobolev spaces, functional analysis were invented after Lagrange, and the miracle is that Lagrange, without knowing functional analysis, conjectured the right results. Okay? Now, why I told you this? Because Lagrange did not know exactly what is a continuous function. He needed to develop the concept. So, for us, a motion is a function which, to every time instant t, associates q of t. I am already fed up of the indices, so I wrote directly q for meaning q1 of t, q2 of t, qn of t. Okay. When it will be necessary, I will distinguish, I will add the index. Okay? Okay. Why we want a motion which is a continuous function? Nobody has ever seen a material particle, for instance, which arrives here and then appears there in an instant immediately subsequent the other one. Is true this? If you have heard about quantum mechanics, you should know that there are particles which are doing very strange things. So in the very moment when we assume that a motion is a continuous function, we are limiting the range of applicability of our model. Do you have heard about tunnel effects of electrons? There are, in our computers, some transistors which work in a very strange way. There are material particles having this amount of energy which go beyond a peak of potential energy, much bigger than their energy. there is a probability of finding the electron which was here to the other side. Okay, we will not try to apply Lagrangian mechanics as it is to quantum mechanics. By the way, it can be adapted, but we will not deal with this. So our function is a continuous function. Now, it is much more difficult to tell you why we assume that this function is differentiable 2 times. Or piecewise differentiable 2 times. And I will try, we will see why later, but it is difficult to tell you now. So we assume that almost everywhere, in the sense of Lebesgue measure, in the time interval, if I tell you something you don't know, raise your finger and tell me that you don't know. I was told that I'm talking to mathematicians, so as I was teaching to engineers for too many years, I will not control myself. So I will tell about Lebesgue measure. But if you don't know what is Lebesgue measure, tell me, and I will try to tell in a simpler way what I want to say. You know, we have the time interval t0, tf, in which the motion is defined. Okay? Tf can be infinity in case. Okay. This is a subset of real numbers. Okay? It is an interval. So you have Lebesgue measure defined on it. If you don't know what is a measure, Lebesgue measure, then you can measure the length of every sub-interval of it. Okay? So we assume that the derivative of q of t can be calculated almost everywhere. In all points of t0, tf, what it means almost everywhere, in the set of t such that q dot does not exist, this set is called to have 0 Lebesgue measure if you can recover it with a union of intervals whose total length is smaller than epsilon for every epsilon. I give you an example. If you have 3 points where the derivative is not defined, you can find always this interval whose length is epsilon over 3, this interval whose length is epsilon over 3, and this interval whose length is epsilon over 3, and you have covered your set with union of intervals whose total length is less than epsilon. And this can be done for every epsilon. Okay? This definition is due to an Italian mathematician, Vitali. Okay? So we assume that the derivative can be calculated nearly everywhere. Why we need some discontinuity of q dot? Because of impulse. Look, I have this. It falls. When it touches, its velocity becomes suddenly 0. So it cannot be continuous, the derivative. And it doesn't exist on one side and the other side. So if you want to include in your scheme impulsive mechanics, then you have to assume that q dot doesn't exist in few points. Okay. Similarly, you assume that you have the second derivative with respect to time. Okay? So the motion is a continuous function which has very often, you allow me this, the first and the second derivative. Okay? This is a motion. Now, think about astronomers who want to study the motion of planets. So, think about the solar system. The solar system is made of the Sun. Then you have Venus, all planets around. So imagine we have 10 planets, 11 planets. How many degrees of freedom you have in your system? If you model each planet with the model of a material particle, you have 3 degrees of freedom for each planet. So if you have small n planets, you have 3n degrees of freedom. Okay. The motion of the solar system is a function which to every time instant gives you the position of every planet. Okay? Okay. You can describe the motion shooting a picture to the system in every time instant, and you say, oh, I have observed this motion. Okay? Now, the problem which we must face is the following. How can I predict the motion before observing it? So this was the big problem which has been solved in a general way by Lagrange, but was not new to Lagrange. Why? Because Aristarchus of Samos, Aristarchus. Okay, I must give you here. It has been called the Copernicus of Greece. Actually, Copernicus is the Aristarchus of modern times. Aristarchus imagined a model of solar system, and he did succeed in predicting the motion of the planets with some basic assumptions. If you like, I can give you the references about this. Okay. Okay, so an engineer, a physicist, a good mathematician, after having introduced the Lagrange parameters and after having introduced the concept of motion, has the big problem of finding a method for predicting the motion of a given system. This is not a scientific model. In a sense, this is a metaphysical problem, not in the wrong meaning of the word metaphysical. Metaphysical means beyond the physics. The physics is what happens if I strike you. Okay, this. A punch, this is physics. Okay. The theory of the punch is metaphysics. Okay, so how can we invent equations such that their solutions gives you the prediction of the motion of a system? This is a big problem. Newton proposed a method. This method doesn't work all the time. So Lagrange proposed another method. And now we have to talk about this method. To talk about this method, we must introduce the concept of functional. So, we have the set of the space of configurations, which is a set of real numbers. Okay? Then we have the set of motions. This is the set of motions, which is an element of the set of motions. It is a function itself. Okay? M belongs to capital M if and only if M is a function which to every t associates q of t. Okay? So the idea of Lagrange is the following. I invent a function which applies to every motion a real number. In set theory, you have studied set theory. In set theory, you have a domain and a codomain for every function. So, let us call action a function which is defined in M having values in R. So the action is what? Is a function which maps every motion into a real number. Now, there is a problem, linguistic problem, because a function which maps a function into a real number, it is not elegant. So, Lagrange introduced the concept of functional. When the domain of a given function is a set of functions, and the codomain is the set of real numbers, this particular class of functions is called functional. Okay? So, which is the idea of Lagrange? We are building it slowly. Look, for preparing this lecture, I needed to go and read the books of Lagrange. Now, it is not difficult, you know. We need to stop other 2 minutes, so I tell you another thing. When somebody is talking or writing in such a way that you don't understand anything, 95% of the times, this person is empty. Clever people manage always to be understood. Why I'm telling you this? If you could read French, consider that the French written by Lagrange is the French of the end of 18th century. He lived at the end of 18th century. He died 1801. Okay. If you read the book of Lagrange, you understand everything. It is crystal clear. And he writes, I'm following what he wrote. So, I repeat for you. First step, I need to describe the configurations. Second step, I need to say what is a motion. Third step, I need to say which is the space of admissible motions. To be precise, I told you that for sure an admissible motion has to be continuous. You need to calculate the velocity, so the derivatives, and you must be able to calculate the accelerations, so the second derivatives. Okay, so in the set of motions you have functions which are 2 times differentiable. Okay, then in the set of motions I define an action which is a functional. This functional maps every function in a given real number. Now, the metaphysical assumptions by Lagrange is the following. Motions are the minimum of the action. If you want to find a motion, you must find the minimization of, you must minimize action. So you must find the minima of the action. Of course, I must tell you in more technical details, but this is the main idea. So the idea of Lagrange is the following. If I am clever enough to find an action functional, to postulate this action functional, to calculate its minima, I have my prediction of the motion of my system. This is the beginning of a big field of mathematical analysis and modern physics. The field of mathematical analysis is calculus of variations, and in mathematical physics we talk about variational principles, which are the principles which drive us in formulating the mathematical models for predicting the physical phenomena. Okay, how many functional exist? You can imagine many kind of functionals. However, Lagrange is rather clever in choosing a particular class of functionals, which we call Lagrange Functionals. This class of functional is very particular, but up to now every classical system is governed by a Lagrangian. Okay? There are some debates about this. Somebody tries to find exceptions, but I mean, my statement is shared with Landau, with Arnold. There are minority people who believe this is not true, just to be honest and to give you a complete vision. Okay? This is not my opinion. This is the opinion of somebody whose name is Feynman, Landau, Lagrange. Okay? Now, for introducing the action functional, I need to do another step. I need to introduce the space of phases. It is trivial. The space of phases is the set of 2n components. The first n is the configuration, and the second is the velocity. Okay? So in a motion, you have a trajectory in the space of configuration and a trajectory in the space of phase, of phases. Okay? Why I need this? Because we call Lagrangian a function which is defined in R2n, in the space of phases, having values in R. So this is a standard function. This is not a functional. It is a standard function, which is called Lagrangian function. Okay? Now, just to allow you to remember in future, Hamilton discovered that a large class of Lagrangian functions can be calculated. How? Considering potential energy minus kinetic energy. I tell you, I will define everything later, but I give you an idea of what we are going to do in future. I will give you examples of Lagrangians in economical systems. Okay? So, a Lagrangian is, for the moment, a function in R which maps elements in R2n in R. Okay. Now I'm ready to show you the Lagrangian action. We told that the action is a map starting from motions, the domain. So Lagrangian action takes a motion and to the motion associates a real number. Okay? Now I must tell you how. So the motion is a function which may associate to every t q of t. Okay. Then we have introduced the Lagrangian function. So the action is defined, the action of a motion is the integral between t0 and t final of the Lagrangian, which is calculated in q of t, q dot of t, dt, integrated with respect to time. So what is doing the Lagrangian? The Lagrangian takes configuration and velocity and associates to this a number. I take the motion. In every time instant, I have a configuration and a Lagrangian velocity. I calculate L in this q dot. This is a real number. I composing L with q and q dot, I have a real function depending on the real variable t. I can calculate the integral of this and I get a number. So the action functional, Lagrangian action functional, is defined in this way. Okay. Now, you understand, this is a very particular functional. Up to now, every mechanical and physical system has been described with a Lagrangian functional. I tell you we'll come to this point, including dissipative systems. It is not true what is said about Lagrangian systems. They are not describing dissipation. Also dissipation can be described with Lagrangian systems. Now the debate is, can every dissipative system be described with a Lagrangian? This is a point we may discuss. But it is not true that dissipation cannot be described with a Lagrangian system. Okay. On the other hand, every conservative system is Lagrangian.
What is dissipative system?
A dissipative system is a system in which the energetic content decreases with time.
So in conservative, everything is conserved.
In conservative systems, the energy, of course, this is not an answer. Okay. Consider motion. We say that a quantity is a prime integral in motion if it is constant along the motion. This you can understand. I know with mathematicians it is better to write a formula. I write a formula f of q and q dot. Okay? I say that f is a prime integral of our motion if f of qt, q dot t, as a function of time is constant. Okay? Now, there is a particular prime integral which is called energy. We will see later. A Lagrangian system is conservative if energy is constant during the motion. Okay? And it is dissipative if along the motion the derivative of this quantity is negative. So it is decreasing. But it is too early. But I wanted to warn you that it is not true that Lagrangian systems are particular systems, or there are some phenomena which cannot be described. Okay, but I'm surprised. Did you study some physics?
Yeah.
Not much. Okay. Okay, because you know, dissipation is a concept which in physics first year they teach you. You know, did you study the trajectory of a projectile? But only without friction with the air, or you added friction with the air? Without friction. Okay. So this is the problem. The prototype of dissipative phenomena are those occurring between a projectile and the air. So when you want to design cannons, you need to take into account the friction of the projectile with the air if you want to reach your target. So you must modify the frictionless equations, including friction phenomena. Okay, but we will try to see this. If this is a common problem, we will try to discuss this in one of the applications of Lagrangian mechanics. Okay, but you have understood what is the action, I hope. Now, the basic philosophical assumption by Lagrange is the following. You give me a physical system whatsoever. Okay. First step, I describe it with a space of configurations. So I introduce suitable Lagrange coordinates. Second step, I consider the set of motions. third step, I must postulate a Lagrangian. Thursday we will discuss about this point, philosophically speaking. Okay. Once you have postulated a Lagrangian, the motion is the minimum of action. So this is, if you like, Lagrange was calling it metaphysics. An Italian follower of Lagrange, whose name is Piola, I will tell you about him because I studied Piola a lot, calls this Lagrangian metaphysics. Let us try to understand this, because this is very important before we do some calculations. Okay? If you have F mass times gravity acceleration equal mass times acceleration. Okay? You admitted to have studied the trajectory of projectiles. You have solved this equation. So, this equation gives you the theory, thanks of which you predict the behavior of projectiles. So this is a theory whose object is physical phenomena. Okay? Lagrange is giving you a theory which is teaching you how to build theories. The object of Lagrangian mechanics is how to build theories. So, in this sense, it is a meta-theory. Now, in mathematics, this happens very often. Group theory is what? Is a theory which allows you to build other theories. Right? So you should not be surprised by this. Now, let us try to understand this point. Do you want to study a physical phenomenon? I give you a standard procedure. You characterize the kinematics, the space of configurations. You characterize the motions. You postulate a Lagrangian. Then everything is mathematics. You must find the minima of action. Okay? Now we try to do this with some mathematical arguments. Now, you said that you didn't study physics. I hope that you studied some mathematics, because otherwise we will be very slow. So, let us think about the problem. I have a motion. I am drawing a motion as a curve in the plane. You must imagine a curve in n dimensions. Okay? The initial configuration is, so imagine that this is time and this is Rn. Okay? You are mathematicians. When I'm drawing this to engineers, there is a noise in the lecture room and students think that I'm crazy. Okay? you are mathematicians, you should understand that I have the Cartesian product of R with Rn, and I'm representing this in a pictorial way. Imagine this curve in n dimensions. Okay. When I talk about minimum, I must tell you where this minimum is attained. If I tell you, find the minimum of x squared, if you are wise, you tell me 0. But if you are wiser, you will tell me where, in which set you are looking for the minimum. Let us plot x squared. If I choose this interval and I ask for the minimum in this interval, then the minimum is attained here. If I ask for the minimum here, the minimum is attained here. It depends on the set. So when somebody formulates a minimum problem, he must tell where he's looking for the minimum. You agree with this? Now, to make an example a little bit trickier, but which is not so, it's rather clever, I think. Imagine to have the function square, and it is defined in the set of rational numbers. Okay? Mapping in R. Try to calculate the derivative of this if you manage. It's not so easy. Why? Because Q is not complete. And all theorems we have studied in calculus require that the set of numbers we are dealing with is complete. Okay? Every Cauchy sequence must converge somewhere. Okay? So, when you try to solve a minimization problem, you must be very careful. The first thing is you must say in which set you are looking for the minimum. So you can imagine that the poor Lagrange, who did not know a lot of functional analysis, could make a mistake in every step. In reality, he was so clever that he found the right results, conjecturing the right properties and making the right choice. So we follow Lagrange so that we don't need to talk about too much functional analysis. So here you have T0, Q0, and here you have TF, QF. So you have a particular motion. This motion starts in a given instant in a given configuration and ends in a given instant in another given configuration. Okay? Now on, we will use also only isochronous motions. Isos in Greek means the same, chronos means time, isochronous means having the same initial and final configuration in the same instance. So isochronous. I will give you lecture notes about this. Okay, but maybe already tomorrow I need to find them in my computer. So I have all motions which start from here and arrive there. Okay, so I have all curves which start from T0, Q0. This is a kind of space-time plot, because you have time and the generalized configurations. Okay, you start from the same space-time configuration and you arrive at the same space-time configuration. Now we can formulate in an appropriate way the minimum principle. The action is minimum in the set of isochronous motions. We will check the spelling, but I think it is the right one. Chronos, isochronous. Okay? Now we can make calculations. And we can transform this principle into equations. I don't know if we will end today, but in any case, tomorrow we will complete this. So how... Wait.
So the isochronous motion should be continuous, or?
But look, don't be confused by my drawing. This is one isochronous motion. This is another isochronous motion. Okay? But I didn't want to cut. I have drawn pictures one on the top of the other. Okay, so I want to say that the motion is totally arbitrary. The only thing is that each starts in Q0, T0, and each ends in TF, QF. Okay? Okay. Now let us stop a little bit and think what we have done for minimizing functions of n variables. Do you remember, I hope, what you have done for minimizing functions of n variables? You have calculated the gradient and you have imposed that the gradient is vanishing. Okay, let us reinterpret this in such a way that we can generalize this approach for functionals. And this is exactly what has been done by Lagrange. So don't be confused. I open here a bracket, a parenthesis, okay? And we study a particular case. Minimization of functions. Then we try to generalize this to functionals. Okay? So if I have the function f of x, and I want to prove that x0 is a minimum for f, what I'm doing? Of course, this reasoning I'm presenting you has been written by Lagrange, then has been generalized. Probably you have seen a generalized version of it. So this is what we can call an heuristic procedure. Do you know what it means, heuristic? Heuristic from the Greek means a reasoning developed for finding. Eureka, I have found it. Eurisco, to find. Heuristic means aimed to find. So it is not, what I'm telling you is not a rigorous reasoning. It gives you the idea of the rigorous result. Okay? So, what we do? We write a Taylor expansion okay. Now, which is the idea? If I know that the second derivative is positive, x minus x0 squared over 2 is positive. Okay? So, fx minus fx0 is positive for every x in the neighborhood of x0 if and only if the first derivative is 0. Because otherwise, what would happen? When x is very close to x0, this animal is negligible. If this derivative is positive, then it is positive on one side and negative on the other side. If the first derivative is negative, vice versa happen. So the only way for having x0 as a minimum is the first variation of the function is vanishing. Okay? Now, think that Lagrange understood what I'm going to tell you when he was 19 years old. The finite variation delta f is f of x minus fx0. Okay? The first variation, delta f, is the smallest term in Taylor expansion of the finite variation, and delta f is f prime x0 x minus x0. The two are equivalent for small variations of x close to x0, otherwise they become different. Okay, all this should be familiar for you. Yes? Now, can I calculate the first variation of action? This is what we have to do now. I don't know if you have studied Frechet derivative. You never studied Frechet derivative. You are from which country?
Ukraine.
Yeah, I believe it. In Soviet Union, they were teaching Frechet derivatives before teaching derivatives. So it could be that you have studied some Frechet derivation. Frechet derivation is the generalization motivated by Lagrange reasoning of the concept of derivative. Okay, so in a sense I'm teaching you how to reach the concept of Frechet derivative with a reasoning passing via history and mechanics. Okay, so if you want, and if we have time and force, you could, it's not compulsory, you could give a small talk about Frechet derivative. I'm giving an example of what we could organize our final test. Okay? And to establish the relationships between Frechet derivative and what we are doing now. Please, come next lecture. Okay? If you don't want to do it, there is no problem. Okay? So what we have to do? We must generalize the concept of first variation. Okay? We have half an hour, maybe we manage. Okay? So, x minus x0 sometimes is called delta x. It's the variation of the independent variable. Okay, now what is doing Lagrange? He considers, instead of x0, he considers q star. Okay, the motion which wants to be the minimum. Okay, the candidate minimum motion, q star of t. Then I am using a small variation of this motion. So I consider q star of t plus delta q of t. So try to make the parallel. Q star is the parallel of x0. Is not x0 because x0 is an element of Rn. You know, mathematicians have lost the capacity of finding similarities. You know, usually mathematicians are blocked. x0 is an element of Rn. Q star of t is a motion. You say they are similar. What are you telling? Okay? So, understand me. When I talk with engineers, they don't mind about precision. They mixed everything, and so it is very difficult to talk with them. When I talk with mathematicians, they cannot make parallels, metaphors, similarities. Try to open your mind. Do you believe that Euler was a mathematician? I hope so. He was very good in making this kind of similarities. Okay? So, you have the motion, you will allow me to draw. Now, you know why I'm pulling a little bit his leg? Because Okay, because I understood it 4 years old. But I didn't invent it. I understood it, which is different. Okay? So try to follow this reasoning, which is not so bad. I mean, it's rather easy even. Integral between T0 and Tf of Lagrangian in Q plus delta Q. I'm not writing depending on T. Okay, I write it one time. Q dot plus delta Q dot, everything depending on T, dt. This is this action, star. Okay? This is by definition the action in the varied motion. Then I have minus integral on L of Q star of T, Q dot star of T, dt, evaluated in T0, Tf. Okay? Now, you are mathematicians, you know that the sum of integral is the integral of the sum. I hope so. Okay? So, you allow me to write this way. Please rewrite this formula. By the way, the problem of minimizing the action has been conceived by Euler, but he could not solve it. The reasoning I'm giving you is the Lagrange solution of the Euler problem. So the final result is usually called Euler-Lagrange conditions. Okay? Now the trick by Lagrange is this one. I have this function of two variables, the same function estimated in varied functions. Maybe now it is better if I write the equation, I write more details. Okay? So this is L of what? Q star 1 plus delta Q1 plus a comma. Q star 2 plus delta Q2, comma, Q star n plus delta Qn, comma, Q dot star plus 1 plus delta Q dot 1 plus Q star dot n plus delta Qn dot minus L of Q1 star Q dot star n. Okay? And this is integrated dt. Okay? You have studied calculus second year. You can write Taylor expansion with the partial derivatives for representing this increment. You have studied calculus second year. Lagrange did not. He was obliged to invent part of this mathematics. Okay? But he was studying in very good schools. He was studying in a Jesuit school in Turin, so they knew very well mathematics. Okay. So, instead of writing equal, now I can write nearly equal. Why? Because I will neglect all infinitesimal of higher order. So instead of writing this increment, finite, I write the first increment. And how do I write it? Integral between T0 and Tf of dl over dq1 delta q1. This is calculated in q star. It is the increment relative to the first variable. Okay? Then I write the increment with respect to the second variable until the nth variable plus dl over dq dot 1 delta q1 dot plus dl over dq dot m delta q dot m plus infinitesimal of higher order, but I've written nearly equal. So this is okay. You agree with what I'm doing or not? Please tell me yes.
Yes.
You know why? Because when I give this lecture to engineers, I need 2 hours for doing this. Because they don't know Taylor expansion. There was a group of 50 engineers who went to the dean for telling that I am crazy. I am using Taylor expansion. So I wanted to teach to you because I wanted somebody who knows what is a Taylor expansion. If you don't know what is Taylor expansion, then I can give up. Okay, I will try to be quickly in retirement. Okay? So you understand what we are doing. Now, I will try to teach you some tensor, some basic ideas of Levi-Civita notation with indices, which is very useful, but not today. But you understand that this is very boring. So I could write in a better way, in a quicker and equivalent way. I could have written this notation like summation over I dl over dqi star delta qi plus summation over I dl over dq dot I delta q dot I. You agree this is equivalent? Yes? It is the same thing with the summation. Okay? However, mechanicians of Lagrangian school, as I am, even this notation consider too much, and we equivalently write integral of dl over dq dot delta q plus dl over dq dot delta q dot. This dot meaning the saturation of the index. Okay? Now, you know integration by parts. I hope. So, let us make a calculation here. d over dt, I will explain you this symbol carefully. dl over dq delta q, q dot over delta q. What it means? d over dt means consider what is in the bracket as a function of time. Okay? And calculate the total derivative with respect to time. Okay? Chain rule, no, Leibniz rule tells you that this is equal to d over dt dl over dq delta q plus dl over dq dot delta q dot. Here is the genius of Lagrange. Can I ask your name? You know, another trick of Demosthenes is to find somebody in the audience and to talk with him. Okay? Can I ask your name?
Sewan.
Okay, Chai Wan.
Sewan.
Okay, Wan. Your nickname is Wan.
But I'm not Chinese though.
You are from?
Bhutan.
Bhutan. Ah. You are Buddhist? You are Buddhist. I like very much the Buddhist philosophy. Look, if I have a function, okay, I can vary it a little, and I get another function. The first and the second functions have the same value, or a value which is very similar, so they have close values, and their derivatives have also close values. However, these two functions have close values, but their derivatives are not close. When Lagrange takes this time derivative and commutes it with delta, he is assuming that the derivative of a small function is small, which is not always true. Do you know who understood how to formulate this in a rigorous mathematical way? A Soviet mathematician in the 60s. His name was Sobolev. He understood that this reasoning lives in the H1 Sobolev space. Okay? So it is really a miracle that Lagrange could find the right trick. By the way, in the original book of Lagrange, he writes 20 pages for justifying this passage and for telling when it is possible and when it is not possible. So let us go deeper in what we are doing. Okay? We are assuming to have a function which is perturbed a little bit in its values, and it is perturbed a little bit in its derivatives. So to say that two motions are close means the positions are close and the velocities are close. Okay? Good. So let us use, instead of this term, the term which we calculate from this equation, placing here minus d over dt dl over dq dot delta q plus. Okay? So instead of this, here, I write plus the total derivative. I don't repeat what is written inside this. Minus d over dt dl over dq dot delta q. Okay? Okay. Which is the value of delta q in T0? 0. Because we have isochronous motions. Delta q is the distance between the motion and the varied motion. Delta q T0 is 0. Delta q T final is 0. So delta q T0 is 0 and delta q T final is 0. Okay? Because of isochrony. Okay? Now, you will not have a crisis, an hysterical crisis, if I tell you that the integral of the derivative is equal of the function to the function estimated in the extrema of integration. This you understand. This is Torricelli theorem. We call it, I don't know, in Russia, maybe they call it Ostrogradsky theorem. Yeah. Torricelli did it before. Okay, take note of this. Okay? Ostrogradsky Torricelli theorem says that the integral of the derivative is the function estimated here, the function estimated in T0 Tf. This function, when delta f is calculated in 0, is 0, and when this function is estimated in f, is 0. So this animal goes away, and we are left only with this. So I resume what we have done. Please understand all this, because this is useful. You understand the mathematics. Delta action is equal to integral between T0 and T final of dl over dq minus d over dt dl over dq dot delta q. Okay? Okay? Now we are very close. Very close. So we'll come back to this next lecture, but we end now because we must end this research. If Q star is a minimum, then the first variation of action has to be 0 for every variation of the motion. So this quantity has to be 0 for every delta Q. You are ready to accept this for functions of n variables, you must accept it for functionals. Okay? Now, my dear friends, which is the function, regular one, continuous one, such that integral of this function times every function v is always 0 for every v? Now, I could use L2 theorem telling that the inner product in L2 of a function with every other function implies that this function is 0. I could tell you that Lagrange roll theorem implies that the only continuous function which multiplied times another function which has zero integral is the vanishing function. You know, the reasoning is very simple at the end. First year calculus. If I have, imagine absurdo that f has a positive value like that. Okay. As f is continuous, it remains positive in a small interval, close to the point where it is positive. Then you consider v, 0 here, triangular here, and 0 out. And this integral is positive, against the assumption that it should be 0. Okay? So, whenever you want to see, independently of the level at which you want to study this result, if you have integral of something continuous times every function equal always 0, this poor function has to be vanishing. Okay, this is trivial for us because we have studied it. This was not trivial. Indeed, Lagrange theorem has been proven for having this consequence. The Lagrange theorem of calculus. Okay. So, imposing the minimum of action imposes that this differential equation is 0. Is valid. These conditions are called Euler-Lagrange minimum condition for the action functional, and these are the evolution equations governing the motion of a Lagrangian system. We will talk about this in the next lecture. Okay? Okay, so we can stop.